Just a quick reminder, we discussed the general theory of line defects / line operators in relativistic quantum field theories, in particular in conformal theories. And then we discussed conformal line operators, our G-flows on line operators. We discussed the G theorem, and then applications to the Kondo line operators, the Kondo defect, and also what's called the thinning field defect. This is the external magnetic field defect that I explained that in 4 dimensions. This is like in the free field theory case, there is some nice phase diagram, and in the interacting theory, there's some other story. We went over that in the previous session over the phase diagram of these various line operators. Are there any questions about whatever appeared before? Okay, and today I'm going to begin with the very pedagogical example of conformal line operators in free U1 gauge theory in 4 dimensions, 3 + 1 dimensions. Then we'll do line operators in scalar QED. Scalar QED is a very nice warm-up to non-abelian gauge theories. So we'll discuss Wilson and 't Hooft lines in free gauge theory, then in the theory with a dynamical scalar field of charge 1, then in non-abelian gauge theory, and we'll end with S-duality. You'll see that there is, I think, a new picture for how S-duality actually works on line operators. So that's the plan. So first we'll do free Maxwell. So I'm going to start from the free Maxwell theory. This is just free Maxwell. I began doing that in the previous, but it was kind of quick, so I'll do it again. So the Lagrangian in the bulk is just free Maxwell theory. This is famously a conformal field theory. Today we're always in 3 + 1. I'm not going to be jumping back and forth. So it's always going to be 3 + 1 dimensions. So Maxwell theory is a conformal field theory in 3 + 1 dimensions. And you can think about essentially 2 types of line operators, or defects in space if you want. One is electric charge with charge Q, and another one is a magnetic charge with charge N. So electric charge with charge Q means that if you integrate the electric field, you get Q units of charge. Magnetic field with charge N means that you integrate the magnetic field and you get N units of magnetic flux. Of course, you can also do something that combines those 2. Those would be called dions. But in free Maxwell, it's trivial. You can just put those 2 on top of each other, and it's not a very, it's not wildly different than what I'm going to say. So to describe the Wilson lines, these are Wilson lines of charge Q, and these are 't Hooft lines of charge N. To describe those, we just write an exponential of IQ and integrate A0 dt. To describe the 't Hooft lines, we don't really have such a nice formula. You can do something, but it's not as neat. The best way to do it is just to say that we put boundary conditions in the path integral such that if you integrate the magnetic field around this monopole, around this line operator, you get N units of charge. So the integral over some small 2 sphere of the magnetic field is just going to be 2 pi times N. Okay, so these are 2 line defects. In both of them you can vary the shape. You can choose a straight line. It's up to you. And they're both actually completely conformal. So both of those are conformal line operators for any. There are conformal line operators for any Q and any N. And you can compute the G function if you like, the G function that appeared in the G theorem. So for those guys, it's an easy computation in free field theory. You just have to consider, instead of a straight line, a circular line in Euclidean signature, find the saddle point configuration for the gauge field, plug it back to the action. So here you get that log of G for the Wilson line is just Q squared, E squared over 4. And for the 't Hooft line, oh, so you can, instead of saying that this is how you define the 't Hooft line. You can also just put a boundary condition on the gauge field in some gauge, so that you just write the formula. It will be actually useful. And so you can just say that the gauge field that corresponds to a magnetic monopole is A equals N over 2, 1 minus cosine theta d phi. This is the famous Wu-Yang, I guess, or Dirac formula for the gauge field in the background of a monopole. Okay, and you can also compute the G function for that, and you get something like n squared over e squared. If you want a little homework problem, you can try to fix the coefficient for the G function of a 't Hooft line. Okay, now famously, there is electric-magnetic duality in free Maxwell theory. So these two are actually exchanged. So you can do a transformation of variables so that the 't Hooft line of charge n is exchanged with the Wilson line of charge q, where q is n. So you exchange basically Wilson line of charge 1 with a monopole of charge 1. This is just electric-magnetic duality. And you have to do it along with inverting the coupling. There's some 4 pi missing here, but just qualitatively. Inverting the coupling constant. And then the G function matches and correlation functions can be mapped. So this is just the restatement of the familiar fact that electric and magnetic sources are interchangeable in free Maxwell theory. And
so you can also work with the dual gauge field. So
yeah, you can write the you can use the dual gauge field to define this as a Wilson line for the dual gauge field. So, but the bottom line is that in Maxwell theory there are infinitely many conformal lines labeled by n and q, and you can also fuse them. And they're all, as I said, they're all conformal, and there is also this electric-magnetic symmetry. But today, the purpose of what I'm going to tell you, what I want to tell you is how this is generalized to theories with propagating matter fields, which is physically much more rich and interesting than the free theory, of course. So I'm going to now discuss scalar QED in 3+1 dimensions. You can do the same with fermionic QED, but scalar QED is easier because scalars are a little bit less subtle than fermions. So the main thing that I'll explain now is how to think about Wilson lines. We'll start with Wilson lines and then we'll do 't Hooft lines. So I'm going to discuss now Wilson lines in scalar QED. So SQED does not stand for supersymmetric QED, it just stands for scalar QED. So what we have to write an action. So I'm writing an action for scalar QED, which includes a kinetic term for the gauge field, a kinetic term for the scalar field, a quartic coupling that I'll normalize in some way that would be convenient. It's going to be written in Minkowski signature. So there will be a minus sign. And okay, this is just scalar QED. What is the vacuum of this theory? The normal vacuum without any defects is phi equals to 0, a equals to 0. No electric field, no scalar field expectation value. But now we are going to add a line operator, a Wilson line operator with charge q. So we deform the action in this fashion. So we have a new, your job as a QFT person is to find the new ground state. You should think about it as a line operator. It's an external defect. It changes the vacuum. You have to find the new vacuum.
No.
Yeah.
The line defect it always added with I, right? Both in equation and something.
Right. If I'm actually, I should have been consistent. I'm sorry. In Minkowski signature, this is the formula. In Euclidean signature, I would have put an I. Yeah, it's very important. In Euclidean signature, you must put an I. In Minkowski signature, you do not need to put an I. Okay? So if I'm actually sticking to Minkowski signature, which is, I think, what I want to do, this is the formula.
What if you take the gauge A is equal to 0 and then impose the Gauss law constraint
it doesn't matter. The physics is gauge independent. You have to find the ground state of this system with a. If you want to think about it physically, you have a charge Q nucleus, which is extremely heavy. Of course, this is going to change the ground state. It's independent of the gauge. Okay?
It's easier to handle.
So this problem, of course, is interacting QFT, and I want to take a limit. I want to simplify it a little bit. So I'm going to take a weak coupling limit. So I'm going to just assume that electric interactions are weak, the quartic interaction is weak, and I'll do some kind of scaling argument where the problem would become classical. Right. So that's a very good point. I was going to get into that. The whole setup that I introduced in the first 3 lectures was when the bulk is conformal, and as Shmuel remarked, of course, the bulk has a Landau pole, there are beta functions. But soon I'm going to take a small coupling limit, where the beta function in the bulk would be next order, so it won't be important. And the reason that this is still useful to do is because the same physics will appear in super Yang-Mills theory, which is actually conformal. So this is a very useful warm-up exercise, even though the bulk has a tiny beta function.
So it's enough here to look at the infrared dynamics?
Yeah, it's kind of enough to look at some low energy limit with non-zero E and lambda. And what you learn from this example would carry over to actually conformal field theories. So to make it precise, let me show you how it works. So you can do a rescaling. I'm going to do a rescaling of the quantum field phi, and this will allow me to define something like H bar. So you could do this rescaling, and then you find the following action. So you have d3x dt minus 1 over 4 f squared plus d phi squared minus lambda over e squared times 2 phi 4. And then I have this q e squared d3x dt delta 3x a0 xt. So it is useful to take a scaling limit where lambda over e squared is constant, is fixed. Lambda goes to 0, e goes to 0, and e squared q is fixed. This is a scaling limit in which the beta function becomes irrelevant. So it's a conformal limit at leading order, because the beta function, if you remember, is of order e cubed. We're keeping lambda over e squared fixed, and we're keeping e squared q fixed. So it's like a limit of heavy nucleus, of a nucleus with large charge. In real life, e squared is like 1 over 10. So if your nucleus is like charge 15, charge 20, this is a good description. Yeah.
Can you also do it for the tooth line? Because
Yes, I'll do it. We'll
Okay.
do it. I'm doing Wilson lines now.
Okay.
I'll try to work out the spectrum of Wilson lines, and then we'll do 12 lines. Yeah. So this is so physically it's a limit where the beta function is ignored, and the charge of the nucleus is like 10, 15, 20. So it's a good limit. Yeah.
Don't the lambda need to be times e squared to get the formula you have in the other board?
Sorry, what?
You need to have lambda times e squared, not divided by e squared.
No, I did this change of variables.
Oh, okay. Sorry.
Okay. So this is nice because we can think about it as 1 over h bar. And now we have a nonlinear differential equation. So the spectrum of Wilson lines boils down to solving a nonlinear differential equation. We have to find the solutions of a nonlinear differential equation, which is essentially the equation of motion of whatever. That's how we do semi-classics, right? We find the saddle point, and then we expand around the saddle point. So the saddle point equation is d mu f mu nu plus j nu equals e squared q delta 0 nu delta 3x. This is just a scalar field and a gauge field around a charged nucleus. Lambda over e squared, phi squared phi. And j is just the usual current. I'll just write the first terms. It should be obvious how to normal. I'm not going to worry about the normalization. It's sufficiently easy to work it out on your own if I did some side mistake. Okay, so it's a nonlinear differential equation. We have to find the saddle points. The saddle point is a useful thing to find because we're going to be able to extract data about the infrared limit of this defect from the saddle point. Okay, so we have to find the saddle point. So who wants to say what is an obvious solution of the system? That's the high school solution of what happens in the presence of a charged nucleus in QED. What is the high school solution of this equation? Coulomb field, excellent. So vanishing phi and the Coulomb field and the Coulomb formula for the gauge field. 4 pi times the distance. That's you can check it's a solution. This is known from high school. And now I'm going to assume that this solution is the correct solution, and I'm going to use it to compute, the properties of the Wilson line. So properties like the scaling dimensions of defect operators, what we call delta hat in previous lectures. So let me show you how this is done. How do I compute scaling dimensions of defect operators? So how do I compute scaling dimensions from this formula? We have a saddle point. To compute the scaling dimensions of defect operators, we must look at how the scalar field phi fluctuates, the fluctuations of the scalar field phi near the nucleus. From the form of these fluctuations, we can read out what we call the bulk defect OPE, and from that we can read out the scaling dimensions of defect operators. Is the strategy clear? So we expand the scalar field phi as a sum over the frequency, angular momentum. It's a sum. It's an integral sum. Just the usual separation of variables. I'm doing it in a little bit more detail, but very quickly, so that you can reproduce it easily if you want. So this is just a general solution for the scalar field in terms of a radial component and an angular component. And now the point is that you have to find the solutions by looking at the fluctuations around the saddle point and linearizing. Okay? So the fluctuations of the scalar field move in a non-trivial background with an electric field. So they are not just exponentials that obey the dispersion relation in flat space. So the very key point is that this function, this is the very key point, behaves in the following way when you go to short distances near the defect. It behaves like some coefficient, which could be a function. What happened to the time dependence? I forgot to write into the I omega t. So when you go to short distances, this goes like some coefficient times r times the absolute value of x to the power nu with L minus a half. I'm gonna now write a formula for what is this nu. L. It's a formula that looks similar to formulas in ADS-CFT. There is a square root, and then there is this contribution from here. You can just verify it by studying the differential equation around this nucleus. Okay, so this is here, mode expansion. This is the behavior near the origin of the modes. This is the exponent that you see. From this, you can immediately read out the dimensions of operators on the defect. How? Because this is the defect operator. Do you remember the bulk defect OP? We expanded bulk operators in terms of defect operators, and the prefactors were the coefficients. So if you think about beta as a defect operator, we can now read out its scaling dimension.
So that for a given L, there would be values of E squared Q where there would be radically different.
That's exactly where I'm going at. You'll see that the solution of a nucleus is not true. That's exactly where I'm going at. So beta is the coefficient of some mode, but you should think about it as a defect operator. So to introduce some very helpful notation, I'll just call it phi hat. You should really think about beta as the defect operator, which is the cousin of phi in the bulk. It's not gauge invariant, so measuring the defect operator, measuring the dimension of phi hat is not good because phi is gauge non-invariant, but measuring the defect dimension of phi dagger phi is good. Anyway, being a little bit sloppy, let me write the defect dimension of phi hat, which I can read out just from this. It's beta. Phi hat is essentially beta. So it's just a half plus nu L. Or if you want to write something that's gauge invariant and not mess with this non-gauge invariant stuff, you just get 1 plus 2 nu L. So this is the dimension of phi near the defect. Now comes the physics. I have to explain what is going on here. So we have a line defect, and we have the phi operator in the bulk. The phi operator in the bulk has dimension 1. So without the defect, phi QED is nearly free, and phi has the canonical scaling dimension of a scalar field, which is 1. But even at arbitrarily weak coupling, when phi comes close to the defect and it turns into, sorry, this had no hat. So in the bulk, the ordinary phi has dimension 1. When it comes near the defect, we call it phi hat. It's a renormalized version of phi. It's a defect operator. And this picks up a huge anomalous dimension potentially, because you see it's very different from 1 generically. For let's say L equals 0, it could be very different from 1. So even at very weak coupling, where the beta function in the bulk is negligible, there is large renormalization of the anomalous dimension when you're close to the defect. So we have to understand what is the anomalous dimension near the defect. So consistency check number 1 is, let's suppose there was no defect. Then E squared Q would be vanishing because Q would be vanishing. L equals 0 is the S-wave mode, and the square root of a quarter is a half. So we would get 1 plus 2 times a half, which would be 2. So delta hat in the case of delta hat of phi hat dagger when there is no defect is indeed 2, which is the scaling dimension of phi dagger phi in free filter. So that's great. But we see that generally speaking, when you have a defect, the scaling dimension goes down. Because this, if you turn this, if E squared Q is like, 0.1, it brings this value down a little bit. And then there is a very special point that Eliezer already observed, where E squared Q over 2 pi is exactly 1. When E squared Q over 2 pi is 1, it means that E squared Q over 4 pi is a half. So this half squared cancels the quarter. And then the L equals 0 mode will have vanishing nu. And something very special happens at this point. The delta hat of phi hat dagger phi hat become exactly 1. So we have a defect operator that has dimension 1 rather than 2. That was the answer in the bulk, even at very weak coupling. But you have to put a big nucleus. So what is, in real life, E squared over 2 pi is 69. That's half of the fine structure constant. So it means that if the nucleus had like charge 68, 69, there will be a marginal defect operator. 1 is a special value because it corresponds to a marginal defect operator. But we cannot really continue beyond that point as of yet. It becomes imaginary and the whole thing makes no sense. So we'll try to approach 1 from below, from above, I mean. Yeah. Yes?
Q equals 0. What's the meaning of the highest value?
Oh, these are derivatives of phi hat.
Why do you have it the right conformal dimension? It's relative this one.
Oh, it's because there is a miracle. A quarter plus L plus 1 can be written as L plus a half squared. So you could take the square root and it's exactly the bulk scaling dimension of a free filter whose spin for the L derivatives. Okay? So there is a small miracle. Thank you. Alright, so we have a marginal defect operator. So in some sense, just to make a weird statement, Wilson kind of was wrong. Wilson never wrote in the formula of Wilson line this piece, but we must add it with some coefficient f times phi hat, phi dagger. So if you don't add a marginal operator, which is invariant under all the symmetries, so the action, then quantum mechanics will generate it for you. So ignoring this operator is sort of wrong if you are interested in heavy nuclei or large charge. Okay, it becomes marginal at some point when the charge is of order like 68, 69, and you have to consider the energy flow for this parameter f. Okay, is that clear?
Can you, in an equal force supersymmetry?
It's the same. It's going to be the
It's
same. That's why I'm presenting QED in a lot of detail, because it's always going to be the same. Also in n equals 4 superannuals, at sufficiently large representations or even smaller representations at large coupling, we'll have to add such an operator and it changes the answers. If you don't include it, you just get inconsistent answers.
What about 5 to the 4?
Yeah, very good. So it opens a Pandora box. What about 5 to the 4? I'll discuss it soon. This is just, I'm just doing something very simple. We see that there is an issue, and we have to compute the beta function of f. So I'm going to tell you what is the answer to that.
Sorry, Steve. When one does, because when one does renormalizations, operators come. Here it will come when you try to make it a conformal operator?
No, it will
So
just appear because
how
it's
will-
marginal.
What calculation will it appear?
Any calculation. So if you take a Wilson line and you try to compute some one-point function in the bulk, it has charge q. You will find that if you do not, you will find that you have to solve these differential equations, and you'll find that there are logarithmic, that you'll find basically some logarithms, which signify that there is some RG flow that is not conformal. You have to tune f to get a conformal fixed point.
Conformality which sets it.
But there might not even be fixed points now.
Because how
You have a
would
new
I have
parameter.
guessed-
You have a new parameter. We don't even know if there are fixed points anymore.
Yeah, but how would I have guessed to put 5?
Well, you
I
can
would
guess it
have
from
thought about
self-consistency. As you have seen, if you did not put this, the answers around that saddle point don't make sense. So you'll have to, you would have encountered logarithms if you didn't put it, which you cannot renormalize without this counter term. It's like in any, QFT, if you don't put some operator which is completely neutral and invariant under all the symmetries, it will be generated in the sense that there would be new divergences that must be soaked up by renormalizing the coefficient of a new
No, my
local
question
term.
was what calculation would I do to
Any
discover
calculation.
that?
Any calculation will have a log divergence that will have to be soaked up by a new counter term.
Okay.
Here you assume that f equals 0 is not conformal.
It's not going to be the conformal fixed point, as you'll see. It depends a little bit of how if there's scheme dependence of like what you mean by f, but in some scheme I'll give you the beta function now. There was, yeah?
Here you had some argument why the beta function is very small, so it's applied only to the bulk.
It's the beta function in the bulk. I just don't want to get involved with the Landau polling QED. But the beta function for f will be very large and significant. I'm just trying to get rid of this question about why scalar QED is conformal. I don't want to deal with that. So this double scaling limit removes the beta function in the bulk.
But usually you have to take into account the 5 to the 4th,
Well, I'll get to it soon.
the 5 to the 4th, and then,
I'll get to it
there
soon.
is some fixed point for,
No,
for
first you have
lambda and E, which we have some special
you're talking about the bulk?
the Coleman, the
You're talking
bulk.
about the bulk or the defect?
No, in the bulk.
In the bulk, I had 5 to the 4 in my action. It's even here. I have this term. It doesn't affect the fluctuations to second order. So it doesn't matter for this computation.
But if you compute the effective potential, there is some fixed point in the bulk.
The bulk has no running in this limit. I'm taking just small e, there is no running in QED. If is 1 over a million.
It is a beta function.
Yeah, but it's 1 over a million, and I'm doing computations with approximation 0.1. It's just the next order. There are some small corrections to the scaling dimensions from the running in the bulk, but they are subleading in the double scaling limit. So the fact that there is a heavy nucleus is much more important than the running in the bulk. You can neglect the scaling limit. Okay, so let me now show you the beta function for f in some convention. So the beta function for f for e squared q over 2 pi smaller than 1 has 2 zeros. Then at e squared over 2 pi exactly equals to 1, it has e squared q over 2, exactly 1, 0, and past that point there are no zeros. So let me just explain. So nuclei below 68, 69 in the scalar QED toy model will have 2 fixed points, actually not 1. So when we wrote this saddle point, we were a little bit careless. But there are two different solutions of this form. They're both Coulomb-like, but they have different boundary conditions for phi near the Wilson line. And there are actually 2 distinct fixed points, and presumably the one that people usually encounter in experiment is the stable one, because the other one has a relevant operator. Here there is a relevant operator. So that's the one that's more like obviously seen, of course, because it's a stable fixed point for the defect. But there are 2 fixed points, so you must include this operator even below e squared q over 2 phi equals 1. Otherwise, you wouldn't see that there are 2 fixed points. So there are 2 conformal Wilson lines at small charge. Then they merge, and then there are no more fixed points. So you don't see any fixed points in this plane anymore. In fact, the coupling f goes to infinity because the beta function has no zeros. So the coupling f goes to minus infinity in this convention under the RG flow. Okay. So what is the conclusion? The conclusion is that there are conformal Wilson lines for sufficiently small q, sufficiently small nucleus, and they have the Coulomb law. And then something happens. There is some phase transition, and the Wilson lines disappear. So you can think about it like in QCD, that conformality is lost for supersymmetric QCD. This is some sort of phase transition. And what did we learn from many years of studying beta functions? We learned that if a beta function drives you to strong coupling, you might have dimensional transmutation. Or in other words, we have to find the new saddle point. Okay, let me just explain where I'm going. So we solved the case of e squared q equals 2 pi and smaller than 1. We found fixed points. We found conformally invariant Wilson lines. But I have to tell you what happens here, because nobody can stop you from putting a heavy nucleus in the vacuum. So you have to say, what is the infrared limit? How much charge do I measure if I make a Gauss surface around the charge? What is the 1-point function of phi dagger phi? I have to answer those questions to tell you the infrared limit. So I have to tell you what happens in this case.
But it could be that the vacuum is not stable.
And it could also be that the vacuum is unstable, like in that example that we saw with the pinning field. So there could be screening is an option, partial screening is an option, vacuum instability is an option. Pair production is a time-dependent process. Here I'm looking at the ground state. What is the ground state in the presence of the nucleus? So you have to find a new saddle point for this nonlinear system. That's the question, and this is the mathematical problem. It turns out that this saddle point is no good, and there is a new saddle point. You have to find it.
Sorry.
Yeah.
So how do you know the beat function for large f?
For large f?
So you do is this a non-put? I mean, it's...
This is exactly in the double scaling limit. We have an exact beta function in the double scaling limit. So the corrections to the beta function are going to be of order e cubed, or e lambda, or e squared lambda, or something of that sort. So in this scaling limit where e squared q is fixed, and e squared goes to 0, we have an exact formula for the beta function. So the corrections are numerically tiny.
So, but how do you arrive at that exact formula?
Oh, you must, so the way these beta functions are computed is by solving this differential equation with boundary conditions that correspond to having this coefficient f. So you think about taking out a small piece of space, replacing it with a charge, something that has overall charge q, and some boundary condition for phi with coefficient f. And then you find the solution of the differential equation. It has some logarithms, and you interpret those as a beta function. So you can read out the beta function from classical differential equations. Or if you want to do more perturbative computations like Nadav and many people did for Wilson lines, you can just compute the beta function by the standard perturbation theory. Lower this interaction, compute logarithms and 3-point functions, and try to resum them. You can resum them in this double scaling limit. So it agrees with the Feynman diagrams. We check that our beta function agrees with just doing ordinary Feynman diagrams. But it's much nicer to do it this way.
So f is also scaled with the e squared, right?
No, f is actually order 1 in this limit. I already rescaled phi, so f is order 1 in that convention. Yeah.
The other solution, what do you have to do?
Yes.
To do the other ADS solution?
The what? Other what?
The other ADS boundary condition is something. You have the.
I just that when we talk about the Coulomb potential and we say that phi equals 0, actually there are two ways in which phi could go to 0.
Yeah.
It could be with Dirichlet or Neumann boundary conditions.
Yeah, but eventually, in terms of the scaling, is it like the two solutions in ADS?
Yes, exactly.
So this is
Yeah,
the
also
root
the reason that the square root formula that I wrote before rings a bell from ADS CFT, it's because this system is conformally invariant to some differential equations for matter fields in ADS2. And the two boundary conditions are like the two quantizations in ADS2.
So this is a
Hmm? Yeah, so the flow here is a double trace flow in ADS CFT language, and you can compute the change of the G function and many things. You can, it's very similar to double trace physics in ADS CFT. But
this could be over the two one is a BF one?
yes, yes, exactly. So if you use this analogy to ADS CFT, this is the BF bound. For a scalar field in ADS2.
I looked at it more as a little Schwinger effect.
Yeah, you can think about it as
Just
Schwinger effect.
more localized than
Yeah.
the Schwinger effect.
So you have to find a new saddle point here, and this is very taxing. Like we do not have an analytic solution, but I'll give you the qualitative features of the solution. So let me plot the electric field times the distance squared from the defect. So of course at the beginning you see q units of charge. So the electric field times the distance squared is just q units of charge. That's the charge that you see when you're close to the nucleus. But then it gets screened all the way to 0. But and in addition, this dashed line is the scalar field condensate. So this is the 1-point function phi dagger phi in the bulk. It turns up and down. It goes to 0 also. So the bottom line is that the heavy nucleus will be completely screened. If you wrap it with a Gauss surface, there will be nothing. You won't see any electric field. So the set of conformal Wilson lines in Scalar QED is up
the
to.
radius of the...
Oh yeah, and you can ask what is the typical scale, and like dimensional transmutation, like in the work on asymptotic freedom in QCD, this generated a huge scale. So let me just write the formula for the scale. It's exponentially larger than the nucleus. So we call it the radius of the cloud. So we call this solution the cloud solution. We have it only numerically. And it's given by the radius of the nucleus, which is like a UV cutoff. It's like in the work of David, he had to pick some UV cutoff to define where the coupling is 1. And then there is an exponent of 2 pi e squared q over 2 pi squared minus 1. So the radius of the cloud, if you put in numbers, like nucleus of charge 70, it could be like 10 to the 15 meters. It could go all the way to the moon, much beyond. So even one atom, which is slightly overcritical, could generate an exponentially large cloud.
So Zohar, you claim that for small q there won't be screening.
For small q, there is no screening, but there are 2 fixed points at least.
So
Because of
this
the
is
questions
the
about.
probability that when you enlarge the charge, suddenly there is something that will.
Yeah, it's because of the Casimir, kind of the
But
Schwinger
at the same
effect.
time, you don't take running of the coupling, right?
There is
Because
there is no
the
running in the
cell
bulk.
is
The bulk there is no running.
So
It's
what
an
is
effect
this-
of the defect.
What is the screening effect? Do you create pairs of?
Yeah. You create
So-
electron positrons in the bulk, which lead to this cloud. But it's stationary. It's not a time-dependent process. It's just the profile of the electron positrons in the bulk.
Have you studied also the fluctuation, like the determinant around the saddle point? Like if it's like the Schwinger effect that you have negative mode and it's dynamical.
We haven't done it in this way. What we have done is we've put these boundary conditions for the differential equation and found the new saddle point, which is different from the Coulomb saddle point. And we assume time independence. we found a time-independent new saddle point with this property. Okay, so this is the story for Wilson lines in scalar QED. Now I'm going to tell you the story of 't Hooft lines in scalar QED. And in the last half an hour, then I'll tell you the way it works in non-abelian gauge theories and how S-duality works. Are there any questions about the spec? Oh, I should say that this is, you could study much more this unstable fixed point. At this unstable fixed point, also quartic operators could become important. So we don't claim to have the full phase diagram of conformal Wilson lines, even in weakly coupled QED, because there could be more fixed points here. We just did an analysis of this coupling, but when you lower the charge, new couplings become important, and we don't have the full phase diagram. We just have some piece of the answer. Okay?
What would happen, you will ask that question, but what would happen if you take Q and minus Q as two charges?
Well, I guess it depends on the distance compared to this scale. That would be the key point.
What it looks like.
You have a new scale in the problem, like in QCD, we have the dimensional transmutation. So everything would depend on the distance compared to that scale.
But can't you consider a Wilson line that connects two charges? That's what you do usually in Wilson line, right?
No, the Wilson line is the world line of a charge. Okay, let me quickly tell you. So this is the spectrum of conformal Wilson lines. Now let me tell you the spectrum of conformal 't Hooft lines in scalar QED.
Quick question.
Yes.
I mean, suppose you started with two of these defects whose charge was not so big, and then you pull them on top
Yes.
of each other, so it becomes very big.
Yes.
Does that mean that the repulsion between them is somehow enormous because you need a huge energy to make the cloud so much bigger?
If you in strictly mathless scalar QED, you could this story that I just told you would also hold for two Wilson lines that add up to supercritical charge. Is that what you asked?
Oh, well, I guess I meant if they're very far away, it's much bigger than our cloud, then there are two small clouds. But if I bring them on top of each other, then the total size of the cloud is much bigger than the
You're
sum.
assuming that each of them is supercritical?
Maybe the sum is supercritical and the
But if
individual is
each of them,
for
if each
example.
one of them separately is not supercritical, it would not generate a cloud.
If then
Only
I
this, but
bring
on,
them close.
bring and flow, but there will be a cloud like on I guess distance scales which are much bigger than the distance between them initially.
Right. So let's say we're in that situation. I mean, does the cloud take a big energy? So it means that the repulsion between them is much stronger because when you push them together with a force, you have to make this big cloud.
But these are external probes,
Yeah.
so we just let them be whatever we want. I'm not computing. I don't have the dependence of the cloud on some on our nucleus. I'm not trying to compute this.
Okay.
I can only tell you the profile of the condensate. Yeah. Okay, so let me tell you what is the physics of soft lines. So it's actually a very similar exercise. You have to try to solve for the dynamics of fluctuating scalar fields around a magnetic monopole. It's almost the same exercise. You have to try to solve the quadratic fluctuations around this background, because this is the naive saddle point. A piece of physics that you should know, I actually didn't know it, but you should know it, is that in classical physics, if you have a monopole, and you just study a charged particle moving around the monopole, it's just in pure classical physics, where you have the Lorentz force and Newton's equations. There is something that's called the mirror effect. So an electric charge and magnetic charge kind of repel each other, so the trajectories are like this. Particles are kind of reflected from a monopole classically. What should it tell you intuitively? It should tell you intuitively that also in the quantum theory, the fluctuations will not be able to penetrate deep into the monopole. And remember that everything, the most important thing was the coefficient, the power of R in the mode expansion. That's what determines the defect dimensions. So I'll soon write a formula that justifies what I'm saying, but you'll see that the classical intuition that particles cannot come close would mean that this power cannot become really negative, and therefore these effects would not happen. There would never be marginal defect operators. So 't Hooft lines would actually be consistent with the naive saddle point, and there is no screening, and they're all conformal. So, but the intuition is the classical mirror effect for scattering of charged particles from monopoles. So I do the same separation of variables. You write the differential equation for the fluctuations of phi around the monopole. And when you're done, you find this formula for the scaling dimension of phi dagger phi on the defect. And as anticipated, you never get anything that is dramatic, in the sense that it never leads to an instability. So that's the formula that you get. You can do, again, a consistent, this is for the S-wave mode. This is for the S-wave. So that's the lowest defect operator, which is a scalar under rotations transverse to the 't Hooft line. You see that when you plug n equals to 0, the 't Hooft line disappears. Again, this is 1 plus 1, which is 2. That's the bulk dimension. So there is no defect that agrees with the bulk dimension. But all the 't Hooft line does is to actually increase the dimension. So even the minimal 't Hooft line, which has Qn equals 1, leads to delta hat equals 1 plus square root of 3. So phi dagger phi is nowhere close to being marginal. And so 't Hooft lines lead to a large renormalization of the scaling dimensions, but you don't get marginal operators and you do not get screening. The original saddle point is the correct one. So, oh, I'm sorry. Q is 1. I was thinking about the charge Q particle moving around the monopole of charge n. So if you want to make contact with scalar QED, just plug Q equals 1 in my formulas.
If we go back to Kobe's question about having two lines with opposite charge, which can be a Wilson loop after all, if you
Okay.
like gauge.
Yes, you can do this setup.
So you can do a square or something.
Yeah, you can connect them here.
Connect
Yes.
it. So what can you say on these, on the tooth and on the?
Well, I'm discussing just the vacuum in the presence of a line like this.
No, but let's say.
I just want to get to, yeah, and I'll discuss it later.
If
Any-
the charges are opposite and you're far away, it's
That-
like having zero
I don't want to discuss it now.
Will you have a perimeter law?
It depends very much if these lines are supercritical. It depends very strongly on whether these lines are supercritical or subcritical, and the distance. But I told you the answer for one line, so it should be easy to figure it out.
Maybe you can use these effects to have an efficient nuclear fusion, you know, if you have a screening effect.
Yeah. Any other questions? So the conclusion for scalar QED is that scalar fluctuations are harmless for monopoles, but scalar fluctuations are dramatic for Wilson lines, and they screen infinitely many of them. You only have finitely many Wilson lines. Is it consistent with electric magnetic duality? Yes, because there is no electric magnetic duality in QED. We have infinitely many unscreened conformal 't Hooft lines, finitely many unscreened conformal Wilson lines.
Because the field is
Yeah. Say again? Yes, it's manifestly consistent because there is no electric magnetic duality in QED. But of course
You
now,
say finite number because there's quantization of,
yeah.
but you are classical, so.
Yeah, because E squared P over 2 pi is limited by 1, so you have only finitely many possible Wilson lines. Q is quantized. Now, let's try to challenge our understanding by going to a theory which is very similar to what I just discussed, but has, we know from the 80s, has electric magnetic duality. So it would be interesting to see how it works. How does it work? So that's actually what I'm going to do now is correct in every non-abelian gauge theory in 4D, but SU2 is the simplest one. I'm not going to write the Lagrangian of Super-Yang-Niels theory. But I'm just going to tell you a story. And the story will be just borrowing results from QED. So let's start from the Wilson lines. Wilson lines are now in some non-representation of SU2 gauge theory. So they're in the S2S plus 1 spin S representation of SU2 gauge theory. So this is the formula for Wilson lines.
Are you at the origin of the?
Yes, I'm always at the origin of the conformal manifold because I want to discuss a conformal bulk theory. Thank you. This is the formula for the non-abelian Wilson line, which SU2 Super-Yang-Niels theory has an SO6 global symmetry, I'm going to discuss only Wilson lines which are invariant. 't Hooft lines and Wilson lines which are invariant under the full SO6 symmetry. There is a huge literature on SO5 invariant Wilson lines because they are BPS. They could be BPS. But I'm not going to discuss them. I just want to discuss the maximally symmetric ones, which are SO6 invariant. So these are the Wilson lines in SU2 super Yang-Mills theory. And the physics is very similar to QED. There are charged particles at sufficiently large spin S. They are going to screen the Wilson line. And you're going to get only finitely many Wilson lines, which are conformal in the infrared. So the formula is that if G Yang-Mills squared times the spin, which appears here, this is the SU2 spin, is bigger than 2 pi, then this Wilson line is completely screened. And why is it screened? Because secretly Wilson made a mistake, and we should have added phi dagger phi SO6 invariant, the SO6 invariant bilinear operator in this, made out of the n equals 4 super Yang-Mills fields. And this would screen all the Wilson lines which have a big enough representation. G Yang-Mills squared is the coupling of SU2 gauge theory. So they're all screened. Okay. Now, this leads to some difficulty, a very important conceptual difficulty, because, okay, we can prove that this is true at weak coupling where this is fixed. This is where our tools of solving these differential equations are true and so on. But let's for a second assume that this is the correct qualitative picture for conformal Wilson lines in super Yang-Mills theory. Namely that at weak coupling there are quite many, but as you go to strong coupling, they kind of disappear. Let me just assume for a second that this is the correct qualitative picture for conformal Wilson lines super Yang-Mills theory. This leads to a contradiction or to some confusion, because S duality tells us that Wilson lines and 't Hooft lines have to be interchanged when the gauge coupling is inverted, if the gauge coupling is inverted. So if at strong coupling this conclusion remains qualitatively true, that there are no Wilson lines basically, it should then be true that there are no 't Hooft lines at weak coupling. And this looks crazy because I just told you that there is a mirror effect, that 't Hooft lines tend to increase the anomalous dimension and they are not screened. They're all conformal in the infrared. So how is this paradox resolved? Does anybody want to make a suggestion?
You hinted something about S duality.
Well, that's what I'm going to explain now. So how is this paradox resolved? The point is that the mirror effect and the fact that scaling dimensions are increased is a correct classical intuition, and it works for bosons propagating around a 't Hooft loop, around the monopole or a 't Hooft loop. I'll give you now the answer for what happens when you propagate gauge fields, spin 1 particles around 't Hooft loops, and you'll see that the gauge fields tend to fall to the center. And this effect of boson instability will be replaced by gauge field instability. So for a 't Hooft line, we'll have to add F mu squared on the line. F mu squared in the bulk is a hugely irrelevant operator. It has dimension 4 or even more at strong coupling. But it will be so much renormalized that on the Wilson line, it will have dimension 1.
So for n equal 2, for example, this won't happen when...
What is n?
N of n equal 4, when the gauge field is not in the same multiplet as the scalar.
No, it's always going to happen. This conclusion will be true in every non-abelian gauge theory. So let me show you how this happens. So I'm going to quote for you the effective potential that is experienced by a particle that's falling onto a monopole. So the effective potential is like a centrifugal, it's a centrifugal potential, 1 over r squared. There is some coefficient which is a half nq. Q is the charge of the electric particle that's falling onto the monopole. N is the monopole charge. And then there is an important prefactor, which is 1 minus g times the spin of the infalling particle. So I have to explain what is g. G is not the Yang-Mills coupling. G is the gyromagnetic ratio, which is This is the gyromagnetic ratio, the gyromagnetic coefficient, and at weak coupling, G is equal to 2. So you can think about G equals 2, because I'm gonna analyze Hooft lines at weak coupling now, and G is equal to 2 at weak coupling, to leading order. So looking at this formula, you see that scalar fields in retrospect were just the case of L equals to 0, and the potential was repulsive. So the scalar fields wanted to flee from the monopole core, and this was the classical mirror effect. But if L is equal to 1, and since G is equal to 2, this becomes negative. So gauge bosons develop an instability, and they become marginal or even tachyonic with complex anomalous dimensions on the Hooft line. So the general conclusion is that gauge fields, that defect operators like F mu squared are not even marginal. If you plug numbers, they actually turn out to be complex. So at Hooft line is not a conformal fixed point. It doesn't even make sense. This saddle point doesn't even make sense in non-abelian gauge theory. It's a true classical saddle point, but the fluctuations of the gauge fields are disastrous. They lead to imaginary scaling dimensions, which is like in the Wilson lines discussion in QED, this is signifying some instability and screening. So in the literature, it has not yet been shown that there is a new saddle point that replaces this saddle point with a completely screened magnetic field. This has not been shown yet, but it should be true that there is some new saddle point with a condensate of W bosons, which screens completely the magnetic charge at the origin.
But it should happen only for some values of n, right? Not for all.
Very good. So for SU2 gauge theory, it happens for all values of n. I'm just going to summarize now, and maybe we'll begin the tutorial session, which Eliezer allowed me to do a little bit before the time. So I'll just summarize how the S-duality works. I'll get to this point of whether it happens at n equals 1 or n equals 2, because it depends on the allowed values of... I'll summarize it in a second. Are there any questions about this point? That it seems that in non-abelian gauge theories, unlike QED, Hooft lines don't actually exist at weak coupling. They're all screened. So now I'm going to summarize how S-duality therefore works.
Can I have some supersymmetric Wilson lines that as the conformal operator and in the S-duality and some closed line?
Right, so there is a question of what happens for the supersymmetric Wilson lines, I guess.
Yeah.
For the supersymmetric Wilson lines, the potential has two contributions. One is from this gauge field, but there is also a scalar field in a supersymmetric Wilson line that breaks SO6 to SO5. And then the potential is different, and there is no instability. In fact, in a supersymmetric Wilson line, there cannot be an instability. By definition, something supersymmetric is the ground state.
Yeah, so we can have some...
So yeah, the way S-duality works on Wilson lines and Hooft lines, which break SO6, is different from what I'm saying, because they're all stable, in fact. I'm trying to clarify how the duality works on non-supersymmetric SO6 invariant Wilson loops and Hooft loops.
The fact that you see that the Wilson lines are screened, is it not just a statement that there is confinement of ordinary charges?
No, this is conformal filtering.
Well, but you said that you can do it also for non-supersymmetric.
This is non-supersymmetric. This is conformal filtering. This screening is screening in the sense of the line defect becomes a trivial operator in the conformal filtering. There is no confinement of anything here. It's conformal filtering.
It's just a leading order, right?
No, it's exactly conformal. This theory is exactly conformal.
No, but I'm not talking about anybody before. Suppose that we do SE2 with no supersymmetric.
But I'm not doing that. My statements are for conformal filters in 4 dimensions. So supersymmetric or not supersymmetric, but conformal filters in 4 dimensions. There are many non-supersymmetric conformal filters in 4 dimensions. What I'm saying is still true for those.
Sorry, for the supersymmetric ones, could it be that the endpoint of the instability breaks the SO6?
Yes, very much so. It could also break angular. It could also break transverse rotations.
So, I mean, could it be this?
It could be that there is a moduli space of screened vacua which breaks SO6 spontaneously. I don't believe this happens, but it could be. I don't believe it. I know almost for sure that the screen solution in this case would break rotational symmetry.
One dimension, okay, break, okay, you see.
It's not like that. It's not really like that. There could be. It's not really one-dimensional. There could be something of the sort that I mentioned. This solution is not known yet, but if I'm just assuming that the answer, because this is complex, that you have screening, I get a consistent picture for S duality, which I'm going to quote. If that's okay. So for gauge group SU2, the following story is true. So these are 't Hooft lines, these are Wilson lines, and this is going to be GN Mills. So there are no 't Hooft lines at weak coupling. And there are many Wilson lines at weak coupling. We found the formula that there are many, many of them. As you go to strong coupling, there is one Wilson line. This is conjectural, of course. And to match this duality, there should be many 't Hooft lines. So the one non-trivial Wilson line is going to be the one that corresponds to S equals a half, because there is a certain, because SU2 gauge theory has a center that doesn't act on anything, so there is one Wilson line that cannot be screened. So at weak coupling there are many Wilson lines. At strong coupling, at most probably just one non-trivial Wilson line. We can see that there are no 't Hooft lines at weak coupling, and probably many 't Hooft lines at strong coupling. This is very difficult to show. But now let's do SO3. For SO3, super Yang-Mills theory. This should be, let me just get the, for SO3, this formula is again true. There are many Wilson lines at weak coupling, and no Wilson lines at strong coupling, presumably. One 't Hooft line at weak coupling. So there is exactly one 't Hooft line for which this is not complex. Exactly one at SO3. Exactly one non-trivial 't Hooft line, and presumably many at strong coupling. So miraculously, somehow this simple analysis of the centrifugal potential of a monopole is smart enough to know that when you plug the numbers appropriate for SO3 gauge theory, you find exactly one 't Hooft line that does not develop an instability. And if you remember, electric magnetic duality sends SO3 gauge theory to SU2 gauge theory, so this miraculously matches. So somehow the weak coupling analysis is smart enough to allow for exactly one stable Wilson line, 't Hooft line. So it seems that, so the emerging picture is that at weak coupling there are probably never any non-trivial 't Hooft lines, or at most one, in SO3 or SU2 gauge theories. In SUN it hasn't been worked out yet. It's only been worked out in SU2 or SO3. And this is basically the phase diagram. Of course, you can try to go much beyond that, because there could be, as I said, that weak coupling there could be many fixed points, and it's not really known. It's just that beyond this boundary screening for sure. Any questions? This is more or less where I wanted to stop and begin the tutorial session, which is what I was instructed to do by Eliezer. So we can smoothly go into the tutorial session. Thank you.
We got some orders from the management. Any questions? So we should thank Zohar again for all the series of beautiful lectures, and then we are allowed to go to the tutorial.